Hi. Okay, so in this video I'm going to talk about elastic potential energy, otherwise known as EPE. And this is the potential energy that an object has due to how much a spring is compressed or stretched from its equilibrium position. Guys, if you're looking at your notes, there's actually a typo on the sheet there. And so you want to change that to what's written here. Okay. So I've got actually a little spring that I brought to the video here. This is a toy, and it's one of those toys where you kind of push it in and it does that. There's a suction cup in here to hold it. And the idea would be that when you have the spring like this and you apply a force to push it in, you're actually storing potential energy in the spring. Okay? And you know that because as soon as you take your finger off, the spring pushes back, and that potential energy can be given to something else and changed into kinetic energy. So that's kind of like the picture that you can think of when you think about a spring. Now, this particular spring likes to be at that length. And that's called equilibrium. And we'll see in just a minute that that position is what we're going to call x equals 0 on a number line. So that when you push the spring and you compress it this way from equilibrium, you're storing energy in it because you're moving in the negative direction from equilibrium. And also, if you were to stretch the string, you're also storing potential energy in it because now you're stretching it away from equilibrium. And what the spring is always trying to do is to get this thing to come back to that x is equal to 0. That's the most important thing you need to know about springs, is that they're always trying to get something to come back to an equilibrium position. So let's look at the formula for EPE. The formula for EPE, and put a box around it, is equal to 1/2 times kx squared. Now, the x is what I was just talking about. X is going to be how far from equilibrium you are. So clearly, the further that you stretch or compress the spring, the bigger that x is going to be, the more potential energy you have. The other thing that shows up in the equation is k, and that k is called a spring constant. And the spring constant is going to tell you how stiff the spring is. So it's a number, and the bigger it is, the stiffer the spring is. Don't worry about the 1/2 and the squared. I'm not going to explain where those come from, but those are part of the formula, so we'll have to use them when we apply this formula. Just like other forms of energy, the units for EPE are also going to be joules. And we can get into the details of that later, but if you multiply the units of k times x squared, you'll end up getting joules. So we're going to use our standard units here when we calculate this. Okay, so a couple of bullet points here. One of them is elastic potential energy can only be positive since position is squared. Okay, so even if the position is negative, meaning you're to the left of equilibrium, when you square that position, it still makes it a positive. So like kinetic energy, elastic potential energy can only be positive. Second point says that the constant k in the formula is called the spring constant, and its units are going to be newtons per meter. We're just going to kind of accept that as fact for now. Importantly, the larger the value of k, the stiffer the spring. So if you have a very stiff spring, you're going to be storing more potential energy in the spring when you compress it because it's stiffer and it's going to store more energy. We talked about the position x in this formula, or the variable x. That's really kind of representing the displacement of the object from equilibrium. And so we talked about that. And equilibrium is the position where the spring does not exert any push or pull on the object. Okay, so why don't we do an example of this to see how it works. It says in the example below, the mass does not detach from the spring. So you have a block here, a 1/2 kilogram. It's on a frictionless surface. I'll write that. You have a spring connecting the block to the wall. The spring constant is going to be 100 newtons per meter. And then underneath you have your number line. And notice that when the spring is at equilibrium, it would be right in the middle. You can compress the spring and push it in to positions B and A. You can also have the spring go out to positions D and E. So let me tell you what this mass is going to do. this mass is actually going to move like my finger. We're going to start off by pushing it into position A, and then we're going to let it go, and it's basically going to go out. It's going to reach a turning point at E, and the spring is going to pull it back, and this is just going to repeat over and over again. So in other words, this is just going to be a repetitious motion of this object going back and forth, but you are reaching a turning point at A and a turning point at E. It's a lot like a pendulum, and it's exactly what we looked at last week in that animation. Okay, so let's do a typical problem here. The first thing I'm going to have you do is actually just divide your page down the middle, and let's say that we want to basically release M from rest at position A. So we're going to have the mass, it's going to be pushed all the way back to position A, and then you're going to let it go. And the question would be, is how fast is the mass going at C? So if you let this thing go and it starts moving, it's going to get faster and faster, and we want to know exactly how fast is it moving when it gets to C. All right, so let's look at this from the energy point of view. We're going to start off by writing kinetic energy at A plus elastic potential energy at A is equal to kinetic energy at C plus the elastic potential energy at C. And I'm going to say elastic here because that's the only type of potential energy that could possibly be changing. Gravitational potential energy will not change because the object is on a level surface. So I'm not even going to worry about that. There's no need to. All right, let's look then and see if there are any easy zeros in this setup. Is there anything here that we can quickly identify as being equal to 0? Let's look over at A, kinetic energy, potential energy, and I hope you can agree that the kinetic energy at A is 0 because the object starts from rest. Okay, so because it's not moving, its kinetic energy will be 0. The potential energy at A, though, is not 0. That's going to be 1/2 k xa squared. And so that's going to be something we would need to know is what that position xa is. When the object passes up point C, it's going to have a lot of kinetic energy. So I'm going to write 1/2 mvc squared. And it's going to have 0 potential energy at C. And that's because C is equilibrium and x is equal to 0. So I'll make a note there, and I'll say x is equal to 0, therefore the potential energy is 0. That's just like the velocity being 0 at A. Therefore the kinetic energy is 0 at that point also. So now what you have is basically just a problem you can solve here. Let's just work out each side. I've got 1/2 times kxa squared, so 1/2 times 100 newtons per meter times the position at A. That's going to be negative 0.2 meters. I have to square it. And that's going to be equal to 1/2 times m times the velocity of c squared. At this point, you can do the math on your calculator. 1/2 times 100 is 50, and you'll have what? 50 times 0.2 times 0.2, that's 0.04. That would be equal to 2 joules. So we have 2 joules of potential energy at point A. So energy conservation would say that all those joules have to go into kinetic form then. And so we say that 2 joules is equal to 1/2 times the mass of 1/2 kilogram times the velocity at c squared. And so then we want to solve for the velocity at c. So this is 1/4. So 1/4 vc squared is equal to 2 joules. Multiply that over. 4 times 2 joules. That would be 8. So the velocity at c is the square root of 8, which is, I don't know what that is. Square root of 8 is 2.8 meters per second. And that's the answer. Okay, so again, write out conservation of energy. All the mechanical forms have to be equal at A and at C. And then look for easy zeros. And then take what you have left and substitute in to find your answer. Okay. Let's do one more variation on this. Let's say what happens if you release from A, but now I want you to find out how fast at D, which is over here. And so at that point the object is still moving, but it's probably slowing down because the spring is pulling it back. So let's set up the energy equation again. I didn't write EPE, but you guys should know that that's what I mean here. But now we're looking at point D, okay, on this side. So it's the same starting point, but now we're looking at from A to D. Kinetic energy at A is still 0 for the same reasons it was before, plus 1/2 K XA squared. By the way, that's still 2 joules. I did the work on that already. And then we're going to set that equal to 1/2 mvd squared plus 1/2 kxd squared. And of course we're trying to solve for the velocity at d. So we'll have 1/2 mvd squared, but we're going to have to add plus 1/2 times 100 times the position at d, which is 0.1, squared. Okay? So now I'm using a different value here. That is not 0. That is not 0. Because I am not at equilibrium here at point D. So I will get 1/2 times 100 is 50. 50 times 0.01 is going to be 0.5 joules. So now I'm left with a math equation here. 2 is equal to 1/2 mass times velocity at d squared plus 0.5. So you subtract 0.5 from both sides. 1.5 joules equals 1/2 mvd squared. The mass again is 1/2. So you'll have 4 times 1.5 square root is equal to the velocity at d. 4 times 1.5 is 6, so this is the square root of 6, and that would be 2.4 meters per second. And that's the answer to that particular question. So if you compare 2.4 meters per second is actually slower than 2.8. That should make sense because we would expect that the mass is going really fast here. That's your 2.8 meters per second. And by the time it gets to D, it's slowed down a little bit. Not much, but it's slowed down a little bit. If you were to go out to E, the velocity at E, I hope you can see would be 0. And that's something you can think about why that might be, but that's clearly a turning point, and so the object has to stop moving in order to reverse direction. Okay? So overall process here, writing out conservation of energy, mechanical forms, and then substituting in to solve to find the thing that's needed after you've identified